Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to electromagnetic theory. In the previous videos we discussed the basic introductory concepts related to electromagnetic theory, and then we discussed about displacement current, the concept of displacement current, which actually started from a confusion related to the application of Ampere's circuital law, and then Maxwell resolved it with the concept by introducing the concept of displacement current. So in this video we'll discuss about the principle, the main principle behind the generation of electromagnetic waves. Okay, the basic principle. So for that we need to review two of the most fundamental laws which are related to magnetic field and electrostatic field. Okay, so first is Faraday's law of electromagnetic induction. Now we have already studied it in electrical machines, and we will be studying it in detail in electricity and magnetism. So I am assuming that you have some basic understanding of this. So Faraday's law of electromagnetic induction is a basic law in electromagnetism which actually relates EMF which is generated, or electric potential which is generated, with respect to the change in magnetic flux linking with a conductor or coil. Coil basically number of turns which is wound over a ferromagnetic conductor. So basically what it states that whenever there is a change in magnetic field or magnetic flux which links with a coil or conductor, as a result of that change of flux there will be an EMF generated which is called as the induced EMF. Okay, so suppose we have a coil or conductor, and here we have a source of magnetic field, be it a permanent magnet or an electromagnet. So when it is either moved to and fro, towards and away from the coil, or rotated, there will be a change in the magnetic flux, or the number of magnetic field lines which pass through the cross-sectional area of this conductor or coil. And because of this change in magnetic flux, there will be an induced EMF resulting in the flow of a current. This is Faraday's law of electromagnetic induction, which can be expressed as this: E, which is the EMF induced, which can be written as line integration of electrostatic field, because electric potential or EMF or voltage can be expressed as line integration of electrostatic field. We have already discussed it in electricity and magnetism. In electrostatics, you can watch that video. And this is basically equal to minus n d phi b by dt, where phi subscript b is the magnetic flux. Okay, and n is the number of turns of the coil or the conductor, the wire which is wound over the conductor, that. So EMF induced is equal to minus n d phi b by dt, and minus sign because the direction of the induced EMF will be in such a way that it will oppose the changing magnetic flux. It will oppose the very cause that produces it. It will oppose the changing flux. That will be the direction of the induced EMF, and this is given by Lenz's law. Lenz's law just puts the negative sign. The magnitude is simply n d phi b by dt. This is Faraday's law of electromagnetic induction. It is particularly used in electrical machines, basically rotating electrical machines, electrical motor, generator, this principle is used. Faraday's law, Fleming's rule, Lenz's law, that it is used. So here this expression is important, this expression, okay, it is very much important. So it is this expression E, which is the EMF, along with the line integration of electrostatic field, which is equal to minus n d phi b by dt, that will use. The second law, which we have already discussed in the previous video, that is Ampere's circuital law, which basically gives the relationship between the line integration of the magnetic field around any closed path encircling or enclosing a current carrying conductor, okay, enclosing a current carrying conductor. Suppose we have a current carrying conductor, this horizontal conductor carrying current I, then the direction of the magnetic field is given by the right hand grip rule, where we imagine the thumb pointing in the direction of the current and the direction of the curled fingers, it gives us the direction of the magnetic field lines. So the line integral of the magnetic field around this enclosing this current carrying conductor, it is mu 0 times the total current enclosed by that magnetic field line. So here only one current carrying conductor is there, so that's why mu 0 I. Actually it is summation of the number of current carrying conductors which are enclosed by that magnetic field line. So here it is only mu 0 I because only one current carrying conductor is there. So this is the Ampere's circuital law which started the confusion, and then Maxwell modified it to this, okay, which we discussed in the previous video, where the line integral of the magnetic field is equal to mu 0 times the conduction current I plus the displacement current ID, which can be expressed as epsilon 0 d phi by dt, which is rate of change of electric flux with respect to time. So this expression is also important, and here mu 0 is the absolute permeability, epsilon 0 is the absolute permittivity of the medium. So if you notice this expression, okay, this expression here, so here if we pay close attention to the two laws that we have just seen here, this is Faraday's law and here the Ampere-Maxwell law, okay. If we pay close attention to these two laws, then we'll see that the first law, it gives us the relationship between electric field, obviously it is line integral of electrostatic field, and magnetic flux, rate of change of magnetic flux with respect to time, okay, electric field and magnetic flux, okay, two different things. One is related to electrostatics, one is related to magnetostatics. And here Ampere-Maxwell law, it gives a relationship between magnetic field, okay, the magnetic flux density, and here rate of change of electric flux. So here electric field intensity and rate of change of magnetic flux, here magnetic flux density, rate of change of electric flux with respect to time. So this is the beauty of these two equations, which gives us the basic principle of generation of electromagnetic waves. So it clears one confusion which existed at that point of time, that electric and magnetic fields, they exist in isolation. No, any change in electric field will cause a change in magnetic field, and any change in magnetic field with respect to time will cause a change in electric field, which is as per these two equations, Faraday's law and Ampere Ampere-Maxwell law. So basically, according to Faraday's law of electromagnetic induction, the conclusion that we can draw is that a time varying magnetic field, it will produce an electric field which will itself change with time. So a time varying magnetic field produces a time varying electric field. And as per Ampere-Maxwell law, a time varying electric field will also produce a time varying magnetic field. Okay, so when either of the fields, either it is electric or magnetic, changes with time, another field, the other field which itself changes with time is also induced in that space. So any change in either of the fields, it produces a kind of electromagnetic disturbance. And one important property of this is that these electromagnetic disturbance, which are in the form of oscillating or vibrating electric and magnetic fields, they occur in mutually perpendicular directions. Okay, they happen in mutually perpendicular directions. So basically, the electromagnetic waves are sinusoidal variations of electric and magnetic fields which are in mutually perpendicular directions at right angles to each other as well as to the direction of propagation of the wave. So suppose we have this electric field which is expressed as per this expression. Electric field is equal to E0 cos kx minus omega t, where E is the time varying electric field, E0 is the amplitude, K is called as the wave number, which is equal to 2 pi by lambda, omega is the angular frequency, and here what we are, as per this expression, it is moving in the x direction, in the positive x direction. The disturbance, it is moving in positive x direction, that's why here it is x with respect to time. And this is the magnetic field. Again, B is equal to B0 cos kx minus omega t, where B is the magnetic field flux density, B0 is the amplitude, again K is the wave number as it is moving in x direction, so x, omega is the angular frequency, and t is the instantaneous time. So what I was talking about is these electric and magnetic fields, they vibrate or oscillate in mutually perpendicular directions. That's it. That is, suppose we take the xy plane. So here the electric field, okay, we have taken electric field in blue, yes, the electric field, it is vibrating or oscillating in the xy plane, okay, it is vibrating or oscillating in the xy plane. So the magnetic field, it will vibrate or oscillate in the mutually perpendicular plane, that is in the xz plane. It will vibrate or oscillate in the xz plane. So electric field in xy plane and magnetic field in the mutually perpendicular plane, which is the xz plane, and both of them, the electromagnetic wave, it kind of moves in the direction of positive x-axis. Okay, so both these waves, the electric and magnetic waves, they are vibrating or oscillating in mutually perpendicular planes and also perpendicular to the direction of the propagation. So here electric field variations happen along the y-axis, see, positive and negative y-axis. Magnetic field variations, they happen along the z-axis, positive and negative z-axis, and the wave altogether is moving in the positive x direction. So electric field y-axis, magnetic field z-axis, and wave propagation along the x-axis. It is not necessary that only the wave can travel in x direction, no. Suppose the wave travels in y direction, this becomes y, okay, so let me clarify it here. Suppose it happens that this is y, okay, this becomes y, then this can become, this will, let's say this stays as z and this will become x, okay. This can also happen, this can become z, this can become, this will stay as y and then this will become x, like that also happen. It is not necessary that only the direction of propagation is along the x and the electric field variations happen along the xy and the magnetic field variations happen along the xz. No, it can happen in any plane, but the thing is that if the electric field, the electric wave, it is contained in a particular plane, then the magnetic field, it will be in the mutually perpendicular plane and the direction of propagation will be perpendicular to both of them, like that. So that is the rule. So this is the electromagnetic waves generation. So the basic underlying principle is the basic understanding of Faraday's law of electromagnetic induction, particularly this expression which relates the EMF generated, which is expressed as line integral of electrostatic field, which is equal to minus EdL minus nd phi b by dt, electric field related with rate of change of magnetic flux with respect to time, and the modified Ampere-Maxwell law, that which relates the magnetic field, the line integral of magnetic field, with conduction current and displacement current, which is expressed as epsilon 0 d phi by dt, which is rate of change of electric flux. So magnetic flux density, electric flux, and electric field intensity and magnetic flux. So it proves that these events, changes in the electrostatic domain and magnetostatic domain, they are not separated, they cannot happen in isolation, okay, they are interrelated. So whenever there is a change in electric field, there will be a change in magnetic field. Whenever there will be a change in magnetic field, there will be a change in electric field. So any change in one particular thing causes an electromagnetic disturbance, which causes vibration in mutually perpendicular planes, also perpendicular to the direction of propagation of the electromagnetic wave. So this is the basic principle of electromagnetic wave generation, which basically obeys the sinusoidal variations. Here I have written in cos format, you can also write it in sine format. There is no problem. You can write sine kx minus omega t, there will be no problem. Okay, so this is the basic principle of generation of electromagnetic waves. Okay, so I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.